Hey guys, so we're gonna do a basic reverse engineering exercise. So I have this DC warm geared motor that I'm trying to fit into my CAD assembly, um, and that's the whole reason of reverse engineering is you can see how everything fits together. The more parts you have in there, the less iterations you have to do on the design as far as fitment. Um, for this exercise, the only thing you need to do is have a caliper. So I have a Mitutoyo 6-inch caliper here. Depending on the job that you're doing, it doesn't have to be like Mitutoyo. It could be like a generic, Harbor Freight, or something you get from Amazon. Uh, Also, if you don't have a CAD software accessible right now, you can just have a notebook and some, pen, pencil ready. So let's get started. So I'm gonna record my screen here. It's already recording. So first things first, you kind of just want to look at the shape of it, really, of how you can start. There's really multiple ways you can start and put this into CAD or start your dimensions. But the most basic thing I see here is the generic shape, the rectangular piece here, the gearbox itself. And the next thing you got to figure out is this metric or standard? And this is a basic Chinese, gearbox, geared motor. So I'm gonna make the first assumption this is gonna be metric, and we can kind of confirm that by taking, some simple major dimensions outside. So here I'm already seeing about, I think it's done on camera, 32.09, and you take multiple dimensions, it gets even closer to 32. So I'm already making an assumption this is going to be a metric part, and it's also already supported by the fact that this is a Chinese gearbox. And then you can take the other dimensions and you see that how close it is to 46. You can also assume that some parts, your part might have a mix of metric and standard dimensions, and I've done that in the past where the generic overall dimension is in metric, but the fasteners are standard, just because how accessible standard fasteners are in the US. So we're already making the assumptions that this is metric, and in my CAD software I'm already gonna set my units to metric and millimeters. I like using millimeters depending on the size of the part that I'm reverse engineering. Sometimes I'll go by centimeters. That's the beauty about metric system. It's just you go by tens, but we'll not make that argument. I use both. So let's get started. So the first thing I see here is the rectangular here. You see some chamfer off, off. It's not 45 degrees, but you'll see a mostly flat surface at the bottom. You have this extrusion. We're gonna try to do that last, but basic dimensions you want to just do. So here we did have 32, I believe. Yep, 32 and 46. So let's draw that on CAD. So I'm gonna sketch it. This is not gonna be a CAD tutorial. You can use any CAD that you want. I heard Fusion 360 is very similar to what I'm using, which is Solidworks, and Solidworks is very accessible to many engineering students, as long as you have a .edu, I think. I'm not sure. So 32 and 46, and then measure twice, cut once. So that's what we're gonna do, just to confirm. Alright, so now we're gonna do the height. So like I said, don't focus too much on the features. You can always do that last. So we're gonna do the features, here, and the flat surface at the bottom. I already know it's gonna be weird. They probably made this and then just added, the lid part of it. And you gotta bear in mind that these measurements, actual measurements, will differ from their spec, just because of a thing called manufacturing tolerance. So your manufacturing tolerance will depend on how good of a quality product you want. And I can already tell you, these cheap gearboxes will have you know, plus minus 1 millimeter, 1.1 millimeter tolerance. So being as far as 0.1 off is not going to be much. So here we're more worried about being close to dimensions of the actual thing versus the spec that they designed here, right? So we'll just follow whatever it says. 22.32. So I'm just gonna do like multiple, you know, go around the parts, see if you're getting the same number. Yeah, 22.3 is what I'm getting. So let's put that. So there you go. You have the basic, you know, gearbox box. It looks like the same thing. And it's going to be up to you how detailed you want the models. You know, you have these features, you have the screws, you have this extrusion here. What I'm going to focus more is the motor and the shaft, so I can place it the best way I can in my assembly. So I'm gonna do this next thing. You can do the features if you want. I usually save those last as long as it's not, you know, interfering with any other dimensions. So what I'm gonna do is I'm gonna start with this. So here you have a threaded, an internal thread, and you can get, I don't think I can get the depth using a caliper here, but I'm gonna make an assumption for those. You know, you can get a screw and kind of see how far it goes down deep, but you can do that later. I'm more worried about the dimensions of the holes, how far they are from the edges and from each other. So a good practice is to have a reference point, and if you learn anything about GD&T, it's always about the reference points, right? So we're gonna define this as our reference, this top part right here. So from the top part, you can measure from here to the features here, the holes. So what I'm gonna do is, first thing I'm gonna do is I'm gonna measure, because I'm gonna be using the outside of these extruded cylinders to measure from the edge, and it's not gonna be perfect because you're kind of like you're gonna be on an angle. Let me see if it focuses here. You're gonna be on an angle like this, so it's not gonna be, you know, straight, but we can make, again, educated assumptions. So I'm gonna measure this first cylinder here, 7.48 is the first one, 7.48. So 7.48, I'm assuming they want it to be 7.5 here, but I'll put 7.48. So it's gonna be on top. So let's see, go on top plane. I'm gonna make a sketch here, and I'm also gonna assume that this is gonna be all symmetrical. You can make that assumption if you want, and then learn the hard way that it's not. And I usually like to risk it and just do that. I've had more chances of risking it and getting it right than not. So you make your basic draft, and then you can set the dimensions of the circle. What did I say? 7.48, right? No, now I'm getting something else. 7.45. That's a safer bet. So 7.45, and the beauty about, you know, CAD is you have all these tools to make it easier for you. So I'm gonna set these as equal to each other, and then you can confirm if this is symmetrical by just you know, doing a rough check around the edges. So I can already tell this might not be symmetrical. And I made the wrong assumption. This is not symmetrical. So we can have to remove any of the relation here. So that kind of makes things complicated. So since it's not symmetrical, what I'm gonna do first is get the spacing, the center to center spacings between the holes, and then I'll align it with the edges, right? So we already know the diameter of these holes. So now what we can do is we can measure the outside diameter from each other like this. You guys can see it. I'm gonna do it like this. So this measurement gives you, so let's say 40.5 is, you kind of, and the best practice here is the smallest number you get is what you have, because you can't get any smaller than physically what you're measuring, right? So, and the cat is being needy. Okay, so I'm getting about 40.5. So what you can do here is you can do a math, like a basic math. You already know the diameter, which is 7.45. I think it's gonna be 7.5. And if you end up doing that, you're basically gonna do this overall like measurement, and you're just gonna subtract one diameter, because you do half, it's one diameter. Basically two radii, it's gonna be one diameter, right? But you can also go to your CAD software and add some points where you did take your measurement, and kind of make it easier for you if you're not a math genius like I am. I mean, I'm not a math genius, that's what I'm saying. So 41.5 is what we measured. Let me just double check that. Or 40.5. So I'm gonna put 40.5 here, and bam, you have this center to center distance already. So like I said, we're not gonna worry about how far it is off the edges yet. We're just trying to get the center to center between the holes. So now we're gonna do this 20.5. I'm assuming 25.53. Yep, 25.5. So I think I should have put the diameters as 7.5, would have made it easier. But we're gonna be doing the extra work of putting those anyways. So 25.5. Alright, so we got those dimensions. So now we're gonna worry about how far it is off the edges, right? And even here you can also start doing the general, you can do construction sketches of like where the shaft is gonna be. So what I can do is, I'm also making another assumption, it's gonna be between these two. It's probably gonna be symmetrical. You can do a quick check. Again, 19.9. Yeah. Yeah, I think it's gonna be pretty much symmetrical. 19.2. Yeah, so I just confirmed this is gonna be symmetric. So I put that in the middle here, and I think this is gonna be pretty. Oh wow, it's not symmetric. Yeah, it is symmetric. So we can assume we already made the assumption that this one up and down and the, I guess, y-axis, right, or z-axis in terms of SolidWorks, that this is going to be along the center. So we can make some no, we don't want to make that coincident. We can already make some relationships here, that it's going to be symmetric along this axis. And now I'm just going to measure from here to the edge. What is it going to be? About 9.3. Like I said, it's not going to be perfect, just because unless you have the additional tools of, you know, propping it against a flat surface and then measuring it between, you know, the space between that's going to be more accurate. But for me, I'm more concerned about just getting this done. So I'm going to make, you know, try to get it as close to the same plane as possible, which you're not going to get because there's a little bit of chamfer or fillet here. So you don't want to get on the fillet itself, you want to stick on the flat surface. So 9.4 is a good, and you can also kind of subtract a little bit if you already know it's going to be off. Because here, if you're going diagonal, you're going to be, you know, you're going to be adding some dimensions there going diagonal. So 9.4 is a good bet, I think. Like I said, I'm just making additional points. This is there's many different ways to do this. I kind of learned on my own. I did some GBNT kind of exercises, but that's more for standard drawings, standardized drawings. As far as reverse engineering, you kind of just do it. You kind of learn with the best practices that you have, and you can see my CAD doesn't look standardized at all, just because I kind of learned it on the fly. So whatever gets the work done, right? So I'm rambling too much here. 9.4. All right. Actually, gonna do 9.5. So we can confirm on the other side what's supposed to be 10.7. So there's some measurement tools here in SolidWorks. Let's see. 10.9. Yeah, so that's about right. That's basically what we got there. 9.5 here. Yeah, so now that we have those cylinders, we can also, we'll do the holes later using the hole wizard. If you want to do the holes now, you can just, draw up the holes. But I'm gonna extrude this, and we gotta define how high they are. So there's two ways to do this. You can either use your depth thing that comes with your caliper, if it does come with one. You have this one here at the end, right there, or you can do this one depending on the feature. So this one's going to be more accurate if you have a more flat surface like the cylinder here. So I got 2 millimeters. Well, you can also do the major measurement here, 2.3, remember, and then you just see what the difference is between 24.3 to 22.3. So that's 2 millimeters, just to confirm yourself. If you doubt yourself like me a lot. So 2 millimeters, that's good. So we have this basic measurement. I'm gonna make an assumption this is gonna be metric, so I'm gonna put the holes already, so you can try to get the major diameter of the threads, or the actual, not the minor diameter actually, because it's an internal thread, and it's 2.36. So I'm gonna make an assumption this is an M3 fastener that goes in there. So what I can do is I can go on SolidWorks and make my whole my M3 holes here, and you can just make an educated guess how deep it is, and then I just see it that it actually goes deeper beyond the extrusion of the cylinder. So I'm gonna make an assumption that it's about 3 millimeters deep, or 4. I'll just put 4 here, how deep it is, and I'm gonna put ANSI metric. It's gonna be an M3, and usually here you can choose between tap drill or screw clearances. Actually, I'm just gonna put screw clearance, because that's I just want it for visual reference. I'm not actually gonna manufacture the part. So screw clearance is going to be your major diameter. So for M3, it's going to be the major diameter, not including the threads. So it's going to look bigger than the actual part, just because it's not including the internal threads. So we're going to do that. Say yes. Okay, so we have that part. So we have that basic part. So now here, what I'm going to do is I'm going to work on the shaft, where the shaft is. I'm going to make an assumption. I know I make a lot of assumptions, right? But I think this is about 5. Actually, I think 6 millimeter. Or from time to time, you want to make sure that your caliper is zeroed. Make sure it's clean. Yep. I just I ran my fingers through it. Now it's back to 0. All right. So I think this one's gonna be a 6. Yep. It's gonna be a 6 millimeter shaft. And as far as features go, we can get started with the base like extrusion here, so I can get the diameter of that, which is 13.23. You know, I'm just gonna be like, you know, whatever. Well, we're doing this for fitment purposes and clearance. So we're gonna just follow what we measure. 13.2 or 13.3. And then we're gonna see how far it is from the edge. I'm seeing 21.5. Again, we're in trying to get whole numbers here, but 0.5 is a very known. Sorry, measurement. 21.5 from the edge to that. Making sure that, yep. And then we can get the extrusion thickness, like the same way you did it for the other one. So here I'm getting 24.3. So is it 24.3? It's hard because it's right. Actually, it's 24 minus 22.3. So the good thing about Solidworks as well is you can do math within the dimension. So 24 minus 22.3, it's going to give you whatever the differences are. So 1.7 millimeter, which is a weird extrusion. Sure, that's fine. I'm also I was thinking if I can just extrude the bottom too, because if it's gonna be the same diameter, why not? You know? But that's fine. We're just gonna do this part right here first, just so we can have the dimension or the position of the shaft relative to the gearbox, you know, or to the mounting holes. So let me actually quickly do this part here. So I'm gonna reference from here, and I think I measured 12.7. Right, and that's centered to the top. So because you know that's where the shaft is. Make another assumption. And making another assumption here, it's gonna be 22.8, so that's about 0.5 millimeter high. Looks good, I like it. Next thing is we're gonna put the shaft. Let's make a sketch on top of this cylinder that we already made. It's gonna be 6 millimeter shaft. How high it is, I don't know. Let's do the measurement. So for this one, it's gonna be fine because you can actually make it perpendicular to the surface by aligning it on the surface of the shaft right here, and then you can see how long that shaft is. 13.85, and take a couple measurements just so you're sure. 13.85 is good. I like it. So we're gonna extrude 13.85 here, and you want to do some. Let me see. And this is also going to be important for me too. The flat part where the key or the set screw usually goes to. It's going to be hard to do. Here, usually I just make a quick measurement from the top using the internal measuring tool. So I'm gonna do here. I'm gonna say this is about 12 millimeters long, and you can see how flat feature is how you can measure it from the diameter or major diameter to the flat feature, you know, 5.5. So it's a 0.5 millimeter flat feature. So you can do an extruded cut on top. Make sure this is horizontal. And I'm doing this pretty fast, but you know, I'm assuming you already know your CAD software. So we're gonna do a cut extrude in Solidworks to make the flat feature. Extruded cut, and we measure what, 12 millimeters? Okay, 90. And I'm just going fast just for the sake of this video. I'm already around 25 minutes. So. What's next? All right, so we got the shaft, we got the major stuff, and it looks pretty good. I don't know if you want this part. I mean, we can do it just in case, but I'm gonna do that last after actually putting the motor. So let's do the motor real quick. So for me, the motor is not gonna be as important. What I want to know is just the major dimensions, and maybe where the man, I forgot my words here. These metal, you know, contacts, connectors are gonna be relative to the position of the gearbox. So sometimes you want to know how it's going to be positioned, so your wiring, you can, you know, kind of route your wires where they're going to go. So here, let's do the motor real quick. What I'm going to do here is I'm going to go to the side where the surface of the surface where the motor is going to be. Create a sketch real quick. Find the motor dimensions, which is going to be what, 24.12. Sure, that's fine. View normal to the plane. Make a random circle. 24.12, and you already know that's accurate because you can see the motor is already like offset the gearbox. You can see some space here on top. That's, you know, it's overhanging on the bottom side. So I'm gonna do the same. So we got that major diameter, but I also want to place it already to know where it's at. So you can mess with how you measure it. So I'm going to measure from the top here, and then I'm going to measure from the bottom of the motor, and everything should be square and parallel, assuming again, but that's fine. This is a cheap gearbox we're trying to measure. 25.3, so that's fine. So let's make some lines or points relative to the center of the motor. 25.3, and you kind of just make the dimensions where you measure it when you do a reverse engineering. So 25.3 here. Great, so we got that measurement. You know, I don't care about this bottom part because that's probably gonna check out. And you can always how accurate you want to be, you can always double check. So now I'm gonna measure how far it is off from an edge here. 25 there. That's fine. Let's do 25. Yeah, that looks great. All right, so we got the position of the motor. And then now we're gonna take the main height of the motor. So you can do this two ways. Again, you can do like a rough estimate using the internal tool measuring internal pipe, or you can do like usually what I do is I measure this. We already know this is 46, right? And then you just measure this part, 77 minus 46, so you can use 77 minus 46, 31. You can either merge this or not if you wanted a different solid body. I don't really care here, so we're just gonna merge it. It looks fine. And you can do quick visual kind of features here. So I already know this is there's like an outer sheet metal here that's not, it's not a solid body, it's a hollow motor, you know. So I'm gonna put this sheet metal overhanging 0.5. So you know what I mean, this is just basic stuff. You're not doing anything critical. So I'm even gonna add that thing in the middle, so we can do sketch from this plane. Make it quick, you know. 6.22, and just extrude that. Let's see how. 2.21, and ta-da! And you can make your basic features like a fillet. And I'm kind of breaking my own rule here. Usually I do all this after. I just wanted to show you guys how quick you can do it. So now I'm gonna do my connectors, just so it's important to me where the connectors are. So I'm gonna do that. I can already kind of assume that it's about, you know, on a 45-degree angle. So it's gonna do so what I'm gonna do actually is, let me see. So I'm gonna do a 45-degree, and you can do this in any way you want. 45-degree, and you want this to be centered. How do I do that? Center to the center, concentric. And I want to make, you know what? I'm going to make the slots. So let's make slots perpendicular to that. Oh, what did I just do? You know, you kind of just do a rough measurement, 6.5. Oh, that's not 6.5, 6.5. And 2.8. No. I don't want that. 2.8. And you know, how far is it from the edges? 4.4. I'll just do it. How far is it from the inside edges? 4.4 minus 0.5. I already know that. And we're gonna quickly mirror that. So we can have it on the other side. And then, is it an extrusion? No, it's a little bit. Maybe we'll do like 0.2 or something. Just so we have some kind of feature point. I'll do 0.1, just so you can kind of visually see it. And then we'll add the connectors here by making a sketch. So what I'm gonna do is I'm gonna do a thin feature. It's gonna make it perpendicular, and I don't really care the exact dimensions of it because this is pretty generic. So I'm gonna do like quick width, and I did make it equal here already in Solidworks. So both of those are gonna be equal. Same. Make it perpendicular to that. Perpendicular to that. And you know what? Fine, let's make it centered. And I'm sorry if I'm going pretty fast. This is all just making sure we're not wasting our time here. If you guys want, I can do some SolidWorks tutorial if you're interested. Just let me know. This is kind of my first time actually doing any kind of videos like this. So we're gonna extrude a thin feature because this is a thin feature. It's about thin is this 0.3. That's crazy thin. So we're gonna do 0.3 millimeter thin feature, going up. I don't know. 3.7, sure. Why not? Ta-da! We got that, and you know what? I'll make the features now. Who cares, right? Put some radius here. Maybe 0.5. Down 5. Yep. I'm gonna make some fillets here. 2 millimeters, maybe 1. It's good. And that's pretty much what I want to do. I don't really care about the chamfer here. What we can, I'll show you how we can do that on Solidworks. It's pretty much just. Oh, you know what? That I did wrong. So I shouldn't. Oh, so the chamfer is only here. If it was here and you kind of want to make it here, it's not going to do it because you have the motor and the gearbox as one solid body. What you can do earlier is you didn't have to merge it, so you can still kind of make a chamfer here. And we got lucky because it's not, the chamfer is only the outer. So let's do chamfer here. The way chamfer dimensions are set depends on your setup. So here you can do like an overall face-to-face kind of dimension, which I'm going to do roughly here. It's going to be 5.22. And a good trick that I've learned. Okay, I'm not going to do that. So I'm just going to do edge. And a good trick that I've learned is I can literally put this against the screen, just see how much of an angle it is, and try to, I know it's going to be off camera, but I'm just going to do that real quick. You kind of just see how you put this, basically this is your screen, and you try to put it as you know, as direct as possible to see the angle of the chamfer. And since this is not going to be a critical dimension, I don't really care. I'm going to make an assumption that it's about, I don't know, 10 degrees, right? It's fine. So I'm gonna do that on all edges, just so you can make yourself feel better. You can also do, you know, the fillets around the corners here, make it look good. I would say 1.5 maybe. Yeah. And see, that's why I hate doing the motor here, because it messes with the fillet. Kind of does a calculation of the motor being there, and that's fine. So we're pretty much done. I mean, you can kind of add the other features that you want. So far I like it the way it is. Yeah, I don't really need any other features that I need to add. You can, you know, even fillet anything visually unappealing to you. As far as that goes, you can even put the screws on the corners, and you can go as detailed as you want. That's the beauty of it. And here I'm pretty much done with this thing. You can do whatever you want with this. You can 3D print it, you can show it to your friends, upload it to a digital library like GrabCAD, which I like doing sometimes just to get back to the community. I do download a lot of their stuff, so the community uploaded stuff, that it's great. It's called GrabCAD Library if you want to Google that. But yeah, thank you guys for watching. This is probably going to be a long, very long video, and I apologize. I'm probably not going to edit it. I'm going to leave it the way it is. But yeah, see you guys next time.